All right, let's get started with lesson 7, weak bases. Now, the base dissociation constant, Kb, like Kc or Ka, always refers to the equilibrium in which a base reacts with water to form the corresponding conjugate acid and hydroxide. For example, let's use B to symbolize a base. So if we have a base, and usually the qualifications for a base is that it has a lone pair on the base that can accept an H+. So in this case, from water. So this is our weak base here. And water is going to be our acid. And the water is going to donate an H+ to the base because of the lone pairs. And since it's a weak base, just like weak acids, it's going to form an equilibrium situation with the conjugate acid and base. So the conjugate acid is going to be Hb+, and the conjugate base will be the hydroxide ion. Okay, so conjugate acid and conjugate base. All right, so since it forms or will form an equilibrium, there's an equilibrium expression here. So the equilibrium expression would be Kb is equal to the conjugate acid times the hydroxide ion concentration over the base concentration. And water is in the liquid form, so we leave it out of our equation. Okay? All right, so what are some characteristics of weak bases? First of all, they only partially dissociate in water, just like weak acids only partially dissociate or ionize in water. Remember that a strong base is going to completely dissociate in water. Weak base will not. Weak bases will establish equilibriums. We must use ice in weak acid problems, and the magnitude of the dissociation is always determined by the value of Kb. So as we've looked at before, Kb, now as the Kb value goes up, the strength of the base goes up. Larger Kb's, stronger the base, just like we saw with Kas. And the larger the Kb, there will be more product favored. The smaller the Kb, the more reactant favored we have. All right, let's do some problems using the ideas of weak bases and ice. Okay, so here we have a problem where we need to calculate the pH of a 0.15 molar solution of ammonia. Ammonia is a weak base. It has a very small Kb value. So we're going to write the reaction for this. So ammonia, NH3. The nitrogen has a lone pair on it, so it's going to react with water. Now, usually if there's no other acid mentioned, then the acid is going to be water in this case, okay? So the base forms an equilibrium with the acid, and since water is donating an H+, we are going to form the conjugate acid of NH4+ and the conjugate base OH-. All right, so again, we're going to set up an ice table because this is a weak base. So we have initial, change, and equilibrium concentrations, okay? So equilibrium expression, Kb, is equal to the ammonium ion, conjugate acid, times the concentration of the conjugate base, the OH, and the ammonia weak acid, or the weak base. These are all aqueous except for water, which is a liquid. Therefore, it's not in the equilibrium expression. We don't worry about it in our icebox, okay? Initial concentration of the base, initial concentration of the product is 0. The change is minus x plus x plus x. Everything is a 1-to-1 ratio. Makes it nice. So equilibrium, it would be 0.15 minus x, x, and x, okay? Now we need to solve for x in order to get the hydroxide ion concentration. By having the hydroxide ion concentration, that will allow us then to figure out what the pH is, all right? So let's go ahead and solve for that. So 1.8 times 10 to the minus 5 is equal to x squared over. Now, because the KB is so small, we can use the approximation method. So we can ignore that x and just put in 0.15 here. And so do a quick math calculation, and you should find that x is equal to 0.00164. Now, the OH concentration at equilibrium should equal the x value. Therefore, the OH minus concentration is equal to 0.00164. All right? So now we know what our OH minus concentration. Now, how can we use the OH minus concentration to find the pH, which is our ultimate goal? Well, we remember that the pOH is equal to the negative log of the OH minus concentration. So we can find the pOH, and if we plug in our concentration there, we find that we get a pOH of essentially 2.79, all right? And then we learned a nifty little relationship that the pH plus the pOH is equal to 14. So therefore, we can take 14 minus the pOH, and that should equal the pH, in this case, 11.21 should be the pH. All right, so for this problem, the pH is 11.21 for this weak acid. All right, so that's essentially it. It's very much like solving problems of weak bases or weak acids, but in this case, if we want to find the pH, then we need to use our relationship that pH is equal to pOH, or pH plus pOH is equal to 14. All right. Let's do one more example problem for you here. We have pyrimidine. Pyrimidines make great weak bases. It has a nitrogen group that has a lone pair on it, so that lone pair on that nitrogen easily can accept a hydrogen or another proton, okay? So again, we want to find the pH of pyrimidine. We're given the Kb value for pyrimidine, so let's draw, or let's put an equation out here. Reaction of pyrimidine, C5H5N. There's no acid listed, so we're assuming that the acid will be water. Equilibrium, our conjugate acid should be this, because the water donates an H plus to our weak base, and that leaves us with the conjugate base of OH minus, okay? Again, this is aqueous, that's liquid, aqueous, and aqueous, okay? So ice table. Initial change in equilibrium. The equilibrium expression for this, Kb, is equal to the concentration of C5H5NH plus times the OH minus over C5H5N. and water is not in the equilibrium expression. All right, so let's fill in what we do know. We know that this is 0.65 molar. We know that our initial concentrations for our products are 0. It's all a one-to-one relationship, so minus x plus x plus x. So at equilibrium, it'd be 0.65 minus x, x, and x. Okay? We need to solve for x in order to get the OH minus concentration we need. Okay? So we need to solve for that x. So we plug it into our equilibrium expression. The Kb value is going to be 1.7 times 10 to the minus 9 is equal to x squared over 0.65. And I can use the approximation method and ignore that x because our Kb value is very, very small. All right, so we do the math and we solve for x, and we find that x is essentially here, looking at this, is going to be 3.32 times 10 to the minus 5 is our x value. And therefore, it must also be the OH minus concentration at equilibrium. Okay, and so now that we have the OH minus concentration, hey, now we can figure out the pH by, again, using our idea. And I'm going to erase this to create some more room here. Okay, we know that the pH plus the pOH is equal to 14. So 14 minus the pOH, which, we got to find the pOH first. Let's go back. Got to find. So pOH is the negative log of the hydroxide concentration. Plug that in for that, and we get a pOH of, let's see, 4.48. Okay, double check my math, verify it. Okay, so that is the pOH, and now we can take 14 minus 4.48, and that should give us our pH of 9.52. All right, so the pH for this particular solution, pH is equal to 9.52. There we go. pH for that problem. So again, these are not overly difficult types of problems, but make sure you use Icebox, plug it into the equilibrium expression, and there you go. All right, let's move on. All right, so what are the types of weak bases that we're going to come across? All right, usually there are two major types for our class we need to worry about. The first one is when you have a neutral substance that has a lone pair of electrons on a nitrogen atom. And some examples would be like ammonia. It's a great example where the nitrogen is, or this ammonia is neutral, and it has a lone pair on that nitrogen. So ammonia has a lone pair that can pick up an H+. Pyrimidine, we just looked at that. That nitrogen has a lone pair on it. Hydroxylamine, there's a lone pair on the nitrogen. And then methylamine on the nitrogen too. Notice they're all neutral, and they all have lone pairs on a nitrogen, and they all can pick up an H+. So for instance, like ammonia, it can pick up an H+, forming NH4+. Okay, picks up that extra proton as it's transferred. Okay, so that's what we're kind of looking at. We can do one more. Let's do let's do methylamine. So CH3 and H2. We have a lone pair on that amine. picks up an H plus from some acid, and we find out we have CH3NH3 plus, okay, because we had picked up an extra proton there, okay. So those are one types of weak bases that we're going to come across. Some other types of weak bases are going to be essentially anions of weak acids that have the ability to react with water. Remember this very important rule. Weak acids make strong conjugate bases that will react with water. Always remember that. It's super important. Again, weak acids make strong conjugate bases that will end up reacting with water. So we have some examples here like hydrogen sulfide ion, HS minus, okay? That's basically a very weak, comes from a very weak acid of H2S, okay? You have the carbonate ion, which has a acid of HCO3 2 minus. So again, all of these have conjugates, conjugate acids that are weak. HClO, weak acid, H2CH3O2. Again, all of these are weak acids, and therefore their conjugate bases are going to be strong enough to react with water. Okay, so let's look at an example here, like for the carbonate ion. We know the carbonate ion, CO3 2 minus, okay, it will pick up an H plus from an acid, and it will form HCl or HCO3 minus. All right. It's interesting that these weak acids that have strong conjugate bases, the strong conjugate bases do have lone pairs themselves to pick up H pluses to allow this to work out. All right. So there's the some different types of weak bases to look at. Okay, so anyway, that is all for this particular lesson on weak bases. Study your notes, prepare for a quiz, and come to class with any questions you have. And that is it for now.